Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Hi, everybody, and welcome back to Bufnagle the podcast, where we talk about all things good and the pursuit of the adventure of life. I'm Rafe, and I'm going solo this week because it's one of those weeks to go solo. Those things happen now and then, and people get busy. But in my new state, these are the things that I do. So thanks for being here. We appreciate you listening, as always. We are very appreciative of the listeners that are out there. Without you, we would just be talking at the walls. You know, you can always reach us at bufnagle@bufnagle.com and send us your comments and suggestions and questions, and just, general letters of praise would be a very good thing. If you have something bad to say, take it, put it on an email and then send it right to the trash can. You can do it, you can do it there on your computer. No need to do it to require us to do it for you. But if you would, please, somewhere on your phone there, or if you're listening on your computer, there's a button for liking or subscribing or giving it 5 stars. Anything you can do to help us spread the word, spread the love, spread the buff, that would be a great thing. We'd appreciate it. Tell your friends to listen. You get a free episode, and we get all sorts of good things too. We get cookies and brownies and ice cream and all sorts of wonderful things happen here at the Buff home office when we get 5-star reviews and smiley stars. So take care of that for us. We would really appreciate it. Well, today we're going to do we're going to start on a task that I think this is going to be more than one episode, because the notes I started writing, they just got longer and longer and longer. But we're going to do a history thing. We're going to do a math thing. And in the end, it's going to lead us to an interesting place. But that's the special part here. We're not telling you where this is going. I know where it's going because I wrote the notes, but those of you out there listening, you may not know the notes. But if you're sitting there thinking to yourself, this seems like this is going to be an episode with a lot of thought and a lot of things to worry about. Well, yes and no. I wouldn't worry too much about it. There's no test. You won't have to remember the dates, but having dates in your head as we're doing this stuff would be most valuable to you. But you're probably sitting there thinking, man, this is going to make me really thirsty. And I'm like, yeah, it will, because nothing like history and mathematics makes you thirsty. So if that's the case, you know what you need? You got it. You need a smoothie. And if you're going to make a smoothie, you need a smoothie blender. And the BlendJet 2 is exactly the blender for you. BlendJet 2 is portable, so you can blend up a smoothie at work, a protein shake at the gym, or even a margarita on the beach. It's small enough to fit in a cup holder, but powerful enough to blast through tough ingredients like ice and frozen fruit with ease. BlendJet 2 is whisper quiet, so you can make your morning smoothie without waking up the whole house. The whole house. It lasts for 15 plus blends and recharges quickly via a USB-C. And best of all, BlendJet 2 cleans itself. Just blend some water with a drop of soap and you are good to go. There's a zillion colors. There's different prints on there. There's you can get, these are awesome little blenders, and you ought to get one, get one for you, get one for a friend. This is the kind of thing you should be doing, taking care of those who are taking care of you. So what are you waiting for? Go to the blendjet.com link in our description and grab yours today. Be sure to use the promo code BUFNAGLE to get 12% off your order and free 2-day shipping. No other portable blender on the market comes close to the quality, power, and innovation of the BlendJet 2. They guarantee you will love it or your money back. Blend anytime, anywhere with BlendJet 2 portable blender. Go to blendjet.com. The link in the description there, and use the code BUFNAGLE to get 12% off your order and free 2-day shipping. Shop today to get the best deal ever. So back to history and mathematics. We're going to start here in the late 1600s. So where are we? 1600s. At the start of the 1500s was the age of exploration, as we've talked about a million times on this podcast. We did some the early 1600s. We had the Pilgrims thing in 1620 there in New England. So fast forward from that maybe 70 years and go back to the European continent, in particular go to Basel in Switzerland, I think that is. And there's a family of mathematicians there. There's some fathers and sons and uncles and all sorts of folks there being mathematicians. And then we're going to start with a guy named Jacob Bernoullis. And you may have heard of. I never know how much people know about this mathematics, but this was like just prior to 1700. So they're wearing big powdered wigs and they're listening to. Was Mozart around then? We're gonna have to do one on music. But anyway, they're wearing big wigs, and they are in Switzerland. And Jacob Bernoullis is a mathematician, and he does a number of interesting things. Back in the 1690s, he discovers the number e, which is the base of the natural logarithm. He discovers that if you take the integers and compute all their fractions, so like their reciprocals, so like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. You take all of those reciprocals and you add them up. That sum is infinite, which is really an interesting thing because those numbers are getting smaller and smaller and smaller. And eventually you're adding really, really tiny numbers. But if, we talked, this had to have been a year and a half ago. We did some stuff on infinity and talking about divergence and convergence and things like that. But if you take that sum and add up 1 over 1 plus 1 over 2 plus 1 over 3 all the way out, that number will get, if you want that sum to be bigger than 5,000, I can tell you how far you have to go, how big n has to be for that sum to exceed 5,000. If you want to cross 5 billion, we can compute how big that sum has to be to cross 5 billion. So for any number you give me, I can tell you how far you have to go out in that sum in order to cross that. But if you don't take the reciprocals, but you take the reciprocals of the squares, so you take 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. Now those are numbers. Now that's a subset, right? I mean, that list is a subset of the other numbers we were just talking about. But it turns out if you take out those ones that aren't in that second list, then that sum of squares thing actually converges. There's a limit to that sum. That sum does not exceed a value more than, let me see how I compute this right here. I know the answer, but I'm going to save it for later. Yeah, I'm going to save it for a couple little bits later. But if you take that sum, that sums to about 1.6, a little more than 1.6. It won't exceed 1.65. So that sum actually is that sum converges, and Jacob Bernoullis in 1690 with a quill pen, maybe a lead pencil, maybe some chalk, he was able to prove that in the 1690s. And a little while later, early 1700s, his son, I think it's his son, Johann Bernoullis, also in Basel, became his student. All right, and Jacob Bernoullis was the thesis advisor, and Johann Bernoullis was he was the student, and Johann Bernoullis got a degree in some kind of sciencey, mathy thing. Back then, he studied a lot of the same kinds of things as his father, Jacob, and he did his mathy thing. And then about 1726, Johann Bernoullis became a professor, and he was a professor at that time, and he had a student named Leonard Euler. Not Euler like the Houston Oilers or like the Edmonton Oilers. Were they a team, Edmonton Oilers? Yeah. Not those kinds of Oilers. Oilers like Euler. Leonard Euler was a student of Johann Bernoullis in 1726. That's the right date for that one. Also in Basel there. And Euler was a superstar. He is like a really, really valuable member of the math historical community. And he did all sorts of things that you would recognize now as standard mathematics. In in the early 1700s. So, we still have the American colonies are still just colonies. We haven't even decided to rebel yet. There's some exploration going on around the world. People are sailing this way and that, learning all sorts of things. The world is I guess blossoming from a desire to know and understand how things work. And in mathematics, guys like Euler were doing all sorts of things. He came up with the notation for the Greek letter pi, for the number pi, the ratio of the circumference to the diameter for a circle. He came up with the notation you recognize from your algebra days, f of x. That notation, that's his invention. That's his part of how he worked. He was the guy who assigned the letter I to the square root of -1. So you may be a little freaked out by that, but I is what they call the fundamental imaginary number. It's a number that if you square it, you get -1, and that's it feels like a made up thing, but it's a real thing, and you can use it in all sorts of mathematics, and it becomes very valuable in solving all sorts of interesting equations. It opens up the world to all sorts of things that will take place further on down the line. He developed. He noted that E was the base of the natural logarithm, and his academic grandfather Jacob Bernoulli had discovered E, and Euler recognized that it was the base of the natural logarithm. He actually proved that the sum of the reciprocal squares is pi squared over 6. So you take pi and you square it, which is something people do every day, right? And you get like 3.14 or whatever that is squared. You're going to get about 9, something a little over 9. And then you divide that by 6. That's where you're going to get about 1.6. My calculator says 1.64493. That's what that sum is going to be. He actually proved that was the number. It was pi squared over 6. And he came up with this. He recognized the relationship. This is wacky stuff here. He recognized the relationship between E, the base of the natural logarithm, I, the square root of -1, and sine and cosine together. And he determined what's typically called Euler's formula, that E raised to the I theta. So you have an angle theta, and you take I times that angle and raise E to that power. That's exactly the same thing. This seems just silly. It's the same thing as cosine of theta plus I times sine of theta. So you get this complex number that it turns out that multiplication in the complex plane is rotation around the origin. That's what it turns out to be. And it's a very interesting thing. At this point, mathematics is it is off the rails. They're doing all sorts of really wacky stuff. And remember, it's only 1726 or so when Euler got his degree. And he's doing all this stuff with square roots of -1, with the base of the natural logarithms. He's tying them together with sines and cosines. They're writing out infinite Taylor series. They're just doing wacky stuff. And I think what you can show is that if you take E and raise it to the power I times pi, so you take pi times the square root of -1, and you raise E to that power, and you add 1 to that quantity, you'll get 0. So Euler's formula there, or Euler's constant, however you want to call that, E to the I pi plus 1 equals 0. It ties together two very fundamental mathematical numbers, 0 and 1, and E, I, and pi all together in one tiny little formula, E to the I pi plus 1 equals 0. That's what Euler did. Okay, this is what these guys were doing in the early 1700s. And to me, it's interesting that there was that this is old stuff. This is not. I remember when I learned these things in high school and in college. These seemed like very. They seemed like they had to be new things because technology is always racing along, right? And these things have to be brand new. But no, these were 250 years old at the bicentennial. This is old news. This was not. And they were doing this before computers, before calculators, like I said, with a quill pen, writing letters to each other, sending them back and forth on, in, I don't know, rolled up little scrolls, sending them on horseback across the English Channel or around the continent, whatever it is. And so that's what Euler was doing in 1726 or so. Now, it turns out that Euler had a number of students, but one of the students Euler had was a guy named Lagrange, Joseph Lagrange. And, I guess technically he wasn't a student, but they spent lots of time writing letters back and forth to each other. And back then, the credentialing system was not quite what it is today. But Euler is credited with being somewhat of an advisor, I guess, to Joseph Lagrange. And if you've taken calculus, sometime in your first or second year of calculus, you will study a thing called Lagrange multipliers, and it helps you helps you do some integrals. Lagrange multipliers do. This was 1750s time frame, and Lagrange also showed that every natural number is the sum of four squares. All right, it's the linear combination of four different squares, and I just learned that doing the research for this thing. And this was 1750. This was a long time ago, and they were doing all sorts of wonderful, interesting numerical things. So it turns out Lagrange had a student. I think you're picking up where this is going now. And Lagrange and a guy named Laplace, named for the Laplace transform, and he's also did a lot of study of tides. He figured out how if you have a ball like the Earth and it's covered in water like the Earth, Laplace figured out if the moon is in a certain position, how the tides will slosh around on the surface of this sphere. So it's like, they were all figuring how to do the mathematics of gravity, the mathematics of forces, this Newtonian clockwork world. They were figuring all this stuff out. So Laplace was studying tides and the Laplace transform for solving differential equations. And it turns out Laplace had an advisor. His name was Napoleon, but he had another student with Lagrange, and his name was Simeon Poisson, a French guy. And Poisson is known for a number of things. He was known in stats. There's a Poisson distribution. If you took some basic stats or maybe some advanced stats, you might have heard of the Poisson distribution. It's a distribution on discrete counts, and I think he invented the concept of a Poisson process. He might have been the guy that showed that if inter-arrival times are exponential, then counts within an interval will be distributed Poisson. But that was Poisson. He did the stats thing. He did a physics thing. There was an argument back then about whether light was a particle or whether it was a wave. And Poisson thought that light being a wave was a nutty thing. And he thought, if you have light and it's a wave and it comes from a point source and it goes out, the light goes out away from that point source as a wave. And if you put a circular, I guess I'll call it a shadow maker, a disk out in front of that, then that light should diffract around that disk, and it should meet up on the backside of the disk. And in the center of the shadow that disk makes, there should be a dot, right? If the wave thing is true, then there should be a dot at the center there. And he said, that's nutty. That doesn't make any sense that there ought to be a dot in the middle of that, a dot of light in the middle of the shadow. So he set out he did that conjecture, and he demonstrated that, there ought to be a dot here if it lights a wave. And lo and behold, they did the experiments. And it's really hard to tell. You have to get a point source of light is a hard thing. You have to take a light source. I mean, this is like Lagrange was 1750, Poisson was 1800. So they don't have lasers, they don't have electricity, they have candles. That's what they got, candles. And I don't know, what else would you use to make light back then? They have the sun, mirrors probably. So you have a nice sunny day in a mirror, you could probably get it to go. Remember to look at the sun. But if you can generate a point source by running light through a very small hole, and the light comes out And you have to worry about when it goes through a hole, it refracts or diffracts. Light kind of bends around. You got to be careful with that. But if you start with a point source and you run it out past this disk, indeed you do get a spot of light. Some people call it a Poisson spot, which is rather ironic because it's because he was trying to argue against it being there. But Poisson did that thing in physics. So he did some physics stuff. He did some stat stuff. He did Poisson processes around 1800. And then he got together with a guy named Jean-Baptiste Joseph Fourier. And you may have heard of a Fourier transform if you've studied any wave analysis or things like that. You've heard of a Fourier transform. Also, in fact, this recording here is being done on a computer, and I'm sure there's a Fourier transform thing going on inside the computer right now. So Fourier and Poisson get together. They had a student whose last name was Dirichlet, Diricchlet. And Dirichlet did some stuff with analysis and functions. They were trying to figure out exactly what is a function. They didn't have the nice definition we have now. And Dirichlet came up with this very wacky, the idea back then was like, to disprove something, all you have to do is find a counterexample. And Dirichlet came up with these, with a very strange function. The function is it's 1 if f of x is 1 if x is rational, and it's 0 if x is irrational. So it's this function that bounces back and forth between 0 as you move from left to right on the x-axis. This function goes up and down really, really, really fast because it's bounced back and forth between rational and irrational numbers. And we talked a long time ago about how many irrationals and how many rationals there were. We did some stuff on countability and non-countability. And it turns out that that's a really messy function. It causes all sorts of problems if you're trying to do integration. But that's what Dirichlet said in the early 1820s. He was talking about these wacky functions and how to make them work. And he got together with a guy named Martin Ohm, whose brother was George Ohm, who, if you've done electronics, you've done volts and amps and ohms. Well, this was Martin Ohm was George Ohm's brother, and George Ohm was the ohm guy for whom we have resistance in ohms. And Martin Ohm did things. He studied the concept of a raised to the b power, where a and b are both complex numbers, right? And that's just it's a very difficult thing to get your head around. But Martin was able to do that. But Martin and Martin Ohm and Dirichlet, they had a student. This is called mathematical geology for what that's, or genealogy for what this is worth. It's not mathematical geology. It's mathematical genealogy. And one of their students was a guy named Lipschitz. And Lipschitz got his degree 1853 or so. And he I learned about this guy in graduate school. This guy's pretty obscure, but he's important for the story. So he did stuff in functional analysis, and he's credited with a thing called Lipschitz theorem, which talks about how some functions converge or some functions do some other things. But that was mid 1800s. So we have a little history here that takes us from the Bernoullis in the late 1600s up through Euler, Lagrange, Poisson, Fourier, Dirichlet, up to Lipschitz in 1853. And meanwhile, there's a number of other things going on the continent. Right back in 1682, so this is about the same time frame as our friend Jacob Bernoulli. There was a guy named Otto Menke, and he was the guy who invented the first scientific journal. Right? Of course there was one, but he did that back in Germany somewhere. He had a student whose name was Wichmanshausen, who is not known for much other than the fact that he was Menke's student, and he connects Menke to a guy with Johann Planer to a guy named Christian Hausen, who did a lot of stuff with electricity. And it turns out that Hausen had a student named Kastner in 1739 who did all sorts of things. He wrote textbooks, he wrote encyclopedias. Okay, keep in mind what I just said. He wrote encyclopedias, right? Early 1700s. There's a crater on the moon called the Kastner crater. and that's named after Abraham Kastner, who was a student of Hausen. Kastner and a guy named Johann Bode, who was an astronomer, they had a student named Johann Pfaff, Pfaff. He was a German mathematician. He had two really smart brothers who were doctors, and Pfaff's, I think it's Pfaff, P-F-A-F-F, Pfaff's claim to fame is he was the thesis advisor of one Carl Friedrich Gauss, who was born 1777. So I think about that. He was born, he was a little baby. Gauss was a little baby at the American Revolution. He was born in Germany, and Gauss was like mega genius, man. He did all sorts of things. He developed, we just talked about Fourier doing the Fourier transform. Gauss came up with a thing called the fast Fourier transform, which is a way to compute the Fourier transform rapidly, right? Without it takes some shortcuts in the mathematics, and it gets you the right answer. He showed that the sum of the first n integers is n times n plus 1 over 2, and he used that as a very little kid in school when nobody else knew what that was. He corrected his father's accounting arithmetic at age of 3. He was into astronomy. He studied surveying. He came up with like I didn't really understand what it was, but I think it's like a sextant that allows you to measure not only the angle of the azimuth, the thing above the horizon, but also a horizontal one too. So you can measure like angles between two things when you're surveying, and so height and an arc out to the left or off to the right. He invented one of those things. He's, like I said, he's noted in magnetism. I don't know if you remember those old CRTs that we used to have for our computers, instead of these nice flat thin monitors we have now. There was a button on it called they would get charged with static electricity because they were cathode ray tubes. And every now and then you would hit this button and the screen would go boom, and it would do this thing where it kind of shift and swing, and it would like reset the magnetic field. I don't even know what it was doing, but that button was called a d-Gauss button. And there's the unit of magnetic field strength called a Gauss. That's how you measure the strength of a magnetic field. That's this Gauss guy. He did optics. He did things with lenses and optics. But the thing he's most known for is a thing called least squares, which is a way to it's a way to solve a problem where you have more equations than you have unknowns. So if I have ax plus by equals c and dx plus ey equals f, then I can solve for x and y that makes that so. It will be an intersection of two lines. But what these guys were doing back in the day is they were measuring planets and stars and things like that, and they were trying to predict, when the moon was going to go up or down. This was 1800, late 1700s, early 1800s, and they were trying to figure out all these things. And they were discovering new planets and stuff, and they were trying to figure out exactly where these things were so they could get good measurements, or get good theory based on good measurements. They would oftentimes have a lot of data and very few equations. So if I tell you that there's a point xy that satisfies ax plus by equals c, dx plus ey equals f, gx plus hy equals I. If I tell you that, there's some redundancy there if I don't measure it with error. But if I do measure it with error, then the question becomes one of how do I come up with the best solution to that? And that's a statistics question. And that is one of Gauss's big claims to fame is the way to deal with this thing we call regression. He came up with this concept of regression, how to minimize the sums of squares of errors. Minimizing sums of squares of errors is the big leap in statistical modeling. And that was about 1800. And everything you're seeing today, everything from everything in data science, from support vector machines to machine learning to AI, all that stuff is sitting on the fundament that Gauss put together around 1800, 1799, he got his degree. So that's Gauss. He's a big name, and that's a guy you should know. All right. So we got Menke. We go through these German guys, Wichmann, Hausen. We have Hausen, Planer, Kastner, Bode. They get us to Pfaff, and Pfaff gets us to Gauss. Now Gauss had a student named Christian Gerling. and he did things with geodetics, which is like how do you measure stuff on a globe. Remember, most of the geometry you probably did in high school, that's all called planar geometry or Euclidean geometry, and that's a flat plane, but the Earth is not flat. It's round. It's very round, but it's not perfectly round. So it gets even more complicated than that. But Girling did a lot of things with geodetics. Girling had a student named Joseph Plucker, who studied cathode rays in the early 1800s. So they had enough electricity to be able to make cathode rays. And he in studying these things, he worked out things for the electron. Right? He was he was instrumental in the discovery of the electron, and that was early 1800s. Remember, no computers, no CT scan machines, no X-ray machines. This is all before that. We got paper, we got pencil, we got a bunch of smart folks sitting around thinking about this stuff, reading, and they're figuring this out. Now, it turns out that Plucker and our friend from before, this Lipschitz guy, they got together and they were advisors when they were both at somewhere on the continent, and they had a student whose name was Felix Klein. And Felix Klein is important in a number of mathematical things that we are going to take up, not today, but next week when we get back to the podcast. And we're gonna keep marching down this or up, I guess, this genealogy tree, and we're gonna see where this leads us, because it's going to lead us to all sorts of people that you have heard of, maybe that you haven't heard of, but you didn't know they were related. So we are going to leave off with Felix Klein. And if you want, you may read about him, and you may do your own research if you like to see where this is going. But that's where we're going to leave it for right now. And we will get back to this next time on Bufnagle the Podcast. And until then, I'm going to ask you to seek the good, to be the good, and to spread the good, and to enjoy the adventure of life.